So why did we go over all that? Well, if you remember the very first video, the very first slide I showed you showed the single cell. That means that we had air that came down and it came up and back, up and over, and then it dropped back down and formed one cell. That's only true if the Earth is not rotating and all the planets made up of water, but that's not. So we add a rotation to it. We add a rotation to it. We add land to it, and we can cause a different variation of heat. Well, what that's going to do is it's actually going to break those cells up. So what happens is this air, as it starts migrating back up, as it rises right here, it's going to go up and it actually will sink and come back down this way. And it will actually break up into 3 different cells. A lot of that has to do with the rotation of the Earth, with the Coriolis effect, and with the different temperatures of the globe. So this is what we really see. We see 3 cells here, 1, 2, and 3, and the very top one right up there. This one's known as the Hadley cell, this one's known as the Ferrel cell, and this one is known as the polar cell. Okay, I'm going to show you a little bit more about these. This is a lot of what has to do with our weather and how we get weather, and also it has a lot to do with our major wind belts. So let's take a look at this next little video here. Let's take a look at the Hadley cell here, or this other clip. Here is the Earth. This would be your north and your south and your equator, of course, and then this is the Earth on its side. So this here is the equator, this is north, and this is south. So the Hadley cell starts right here at the equator, and what it will do is it rises up and it will come back down and it will sink and come back. Okay, and if you notice this, the 0 is a mirror image. So whatever happens here, the opposite happens down here, or a mirror image of it. So this one is going to go this direction and this one is going to go this direction. That is the Hadley cell. So now let's take a look at what's going on right here. Since we have air that's rising right here, this is a low pressure. So we have a low pressure right here. Low pressure means that the air is going up. If you remember, the best way that I can think of doing this is, I told you, if you have your arm, air that's sinking as it pushes down on the surface, that's high pressure because I'm applying force to my arm here. That is high pressure. If I pull my finger away, the pressure is going to be reduced, and that's low pressure. Now the pressure is dropped. So air that's rising, going up, is low pressure, and air that's sinking is high pressure. So right here, we would have low pressure. Low pressure always means clouds, because the air is not stable. If we have air that's rising and going up, then the air is not stable. And anytime we can get air to start to rise and go up, we bring moisture, we bring temperatures, heat, and we bring a lot of that latent energy. And once we get up to this point here, bam, we can start making those clouds. We can start making those clouds to form. And usually in low pressure areas, what are we going to get? Cloudy, rainy type weather. And the equator is completely like that. Lots of clouds, lots of rains. We've got a lot of tropical rainforests. We've got a lot of different things that are going on there, all because it's a low pressure zone. Now that's the Hadley cell. Let's go to the next one. Let's go to the Ferrel cell. The Ferrel cell is the next one up. So I have the Hadley cells right here. And by the way, if you're wondering, it's called Hadley in the north and it's called Hadley in the south. It doesn't make any difference. They're both the same. It really is a mirror image of what's going on here. If it's Ferrel cell up here, then it's Ferrel cell down here as well. So the Ferrel cell is the next section. So as the Hadley moves around this way, when that air comes down, it's going to form a high pressure area right here. We're going to have a high. That means air is sinking, and as air is sinking, then that means no clouds. The air is stable. The atmosphere is stable in that area, and there's no clouds forming. So air is actually sinking. It's dry. As air starts to sink, it dries out. And since there's no clouds, these areas are typically kind of your sunny, clear skies, and it's drier. It doesn't mean that it's warm. Just because the sun's out doesn't mean it's warm. It can still be cold. So guess what we find mostly in the 30-degree north and 30-degree south latitudes. This is where we're going to find most of the world's deserts because they're high pressure zones. We live about right here, about 40 degrees north latitude. So we're right here. We're right on this downward spot, which makes sense because you go down to southern Utah, it looks very deserty. And as you start going further north, what happens? The desert starts to not be so deserty, start getting more mountainous. I mean, it's still dry, but it doesn't quite look the same as it does down in the southern portion of the state. So Utah is the southern half of this drier area, and as we start to go up, we start getting into more of that wet climate. These are known as the Ferrel cells. You have one that's on the southern hemisphere, we have one that's on the northern hemisphere, and it's going to, as that air drops, the reason why we have this, the air can either go north or it can go south. And so some of it will go south and some of it will go north. And as it goes north, I didn't mention this before, but you notice that the arrow here is blue. That means the air cools down. As it cools, it sinks. But then, why does it turn red? Well, air takes on the characteristics of the ground that is below it. So if the ground is warm, and we've talked about this, what actually heats the air? It's the earth. It's not the sun, it's the earth. So you would expect that as this air right through here, we'll go down the southern hemisphere instead of north, as it hits the ground and starts moving and migrating across that ground, it's going to start picking up energy. It's going to pick up heat. It's going to pick up water. It's going to pick up all different kinds of things. And as it starts to warm up, you also got to realize too, it might not be as warm as the air down here, but the air in the atmosphere is going to be cooler because we're starting to go further north. So all we have to do is have warmer air than what the atmosphere is, and it will begin to rise. So what happens is that it begins to rise, and it will migrate this way. Now, you can see right here, it either migrates south or it will migrate north, which means this area, if I have rising air, what do I have? Remember? Pushing down is high, moving away is low. What's associated with low pressure? Low pressure is clouds, cloud formation, rain. Okay, that should make sense. So when we come up here, we're getting up into this northern region, and what do we get a lot of? We start seeing more storms. So we start getting up into maybe like Spokane, northern part of Montana, Washington. You start getting up into Canada, and what do you get? You start getting a lot more rain. You start seeing more lakes. You start seeing more water. Okay, we start getting into these subtropical regions. So down here we have tropical, we have desert, arid regions, and then we have subtropical regions. And that's pretty common. You go, and those of you who've been up in Canada, it's pretty foresty, wet, subtropical rains. Okay, it's not hot, but it is wet. Okay, so this is the Ferrel cell. So we have a low pressure, and then we have a high pressure, and then we have a low pressure. And it's true down here. This is where the majority of our deserts are going to be. Now, let's take a look at the polar cell. So the polar cell, we saw that right here we have a low pressure. The air is going to rise, and then it's either going to go down south or it will go north. And as it goes north, it will cool down and then drop. And then as it moves back down, it will warm back up and do the cycle again. But what do you see right here? We have air that's sinking. And since we have sinking air, what does that mean? That means that we have right here, we have a high pressure. So we have a high pressure area. High pressure means clear skies and dry. So what are the poles? Well, guess what? The poles are cold deserts. It doesn't snow a lot there. Most of the time the sky is clear, and that might be opposite of what you think, but it's actually a dry, cold desert. It may look like it's snow. It's just because it's cold and that snow doesn't melt, and it's super, super, super windy. It is very windy up there, so a lot of that stuff gets blown around. Not necessarily storms, but when it does storm there, it does stay. So we have the northern hemisphere right here. This is a high pressure zone, and that means we're going to have sunny weather and clear skies. We get right here, we have a low, and that low means air is rising, and we're going to end up with some cloudiness and rain. We get over here, and we have a high pressure area, and that high pressure area means sunshine, which also means clear skies, because in order to have sunshine, you have to have clear skies. And then we get over here, and we end up with a tropical area. And the same is true as we go further north. It's totally a mirror image. So if we go from right here down, everything to here, it's a book match. So if we fold it back up, it will look just the same. That's what we call a book match. Not the match you light. A book that you look at. We're looking at a book match. Okay, this is the polar cell. Remember, we got the polar cell here, we have the Ferrel cell, and then we have the Hadley cell. These are the three main global cells that we find, and they go all the way around the globe. Okay. Let's see what's on my next slide here. Okay. This slide that you see here, I have got right here. You can see that we got the Hadley cell going on right here. Okay, so this Hadley cell, this is something that you're going to have to pay attention to. If I go back, let's go back here. First of all, the first question is why in the world does this cell stay right there all year long? And the answer is no, it doesn't. It moves. Why does it move? Well, you got to go back to this portion right here. Why is the air rising right there anyway? That's because you're at the equator, and the equator is going to receive a lot of energy, and so that air is going to rise. If you remember, we went back, you notice that the very first one I showed you, oh, it was really warm and through this area, and the air rises, that single cell model. Well, this right here is going to receive the most amount of heat. But it only does it during the spring and the fall, when, if you remember, the sun is directly over the equator in the spring and the fall. June 21st is our first day of summer here. The sun isn't over the equator. The sun is actually right here. Okay, it's more north. It's actually right here, the 30-degree north latitude, or 23.5 degrees. Sorry, it's about right here. So that means this area here in our summertime is receiving more heat. So what would you think the air would start doing right here? It will rise. So what do you think the cell actually does? It migrates. And then as winter comes around and that sun starts shining down more here, guess what that cell is going to do? It's going to migrate back down this way, and it keeps moving back and forth. So this part right here is going to follow the sun. So as that sun moves, this moves along with it. And as that sun moves back down, it's going to move along with it. Same with these other cells. They're going to scrunch up, they're going to expand, they're going to change. So that's what I have right here. Now I want you to watch this animation here. We're going to show you this. So I've got the Hadley cell. Down here I have the year. Okay. Watch what this Hadley cell does as we go through the year. All right, let's do that again. And I should hide the precipitation here. Okay, so what do you notice? We get right here. All right, so let's go back here to July. Let's back this up. Or right here, June 21st. You'll notice that the Hadley cell right here has migrated up to about 23.5 degrees or so. Okay, it's probably a little bit farther than this. But you'll notice that this is the more warmer regions. And so what's going to happen? These cells are going to migrate north. But as I move this down here to December, watch what happens. These cells will drop down with it because it's always going to follow that sun. So if I move this down, we're going to go and move on down. Okay. Perfect. And we'll do this one more time. Migrates up, and then it migrates down. Okay, now something else I want to show you with this as well. We're going to add the precipitation in here again. So you can see here's our precipitation. You can follow the chart over here. Watch what happens to our precipitation as we move through this. Let's go ahead and we'll hit play. Okay, what's interesting is watch these blue ones here. Lots and lots and lots of rain, okay? Greater than 150 millimeters per month. But look where they're located at, right here, okay? Remember, thunderstorms right here. Watch them as they move. As this moves up, watch what happens to those. They'll migrate with it. Okay, hopefully this will make some sense as to why some areas get dry and then they get wet, and they might call it the rainy season or the dry season. It's just because that cell's moving around and doing different things. Okay, let's move on here. Okay, this is taking a little bit longer than I wanted to, but we've got to do this. If you need, you'll just have to take a break. Okay, so ideal pressure systems. Let's take a look at this and we'll take a look here. Now, because of that wind, as it moves through here, it's going to rise up and it will sink, and then it rotates to the right. Remember I had that globe out here and I was turning it? Well, it's going to rotate to the right. This, as it moves from here this way, it also rotates to the right. And you might... I didn't go over this. Coriolis effect is a little trickier than what we think. Why in the world would it do this? Why? This is surface wind, by the way. This is not wind up above. This is surface wind. So as it lands here, as the earth rotates this way, we're going to get that wind and it's going to rotate in this direction. As it falls down here and it goes north, it rotates to the right as well. And the question is okay, why is it doing that? Because really, if I was to bring that globe out and rotate the globe underneath it, it will actually rotate this way. So why does it rotate to the right again? This is where you've got to remember the other part that we talked about this, is that up here, we're traveling 0 miles an hour. Down here, we're traveling at over 1,000 miles an hour. So this is just me, guys. Have you ever been in a moving vehicle and thrown an object out of a window and try to hit something, maybe like a stop sign or maybe that annoying neighbor kid with a water balloon or something? Well, can you hit your target? Yes, but you don't throw it directly at him. You actually have to throw it in front of the target. Because as you throw that target, so what's going to happen is if you're moving in this direction and you're throwing 90 degrees to your direction, then what happens? The object will actually move between both of those, and we'll get this, it's not 45, but it will go between the two. So it will go this way, and your object will go that way. So what happens here is that you've got to realize that as that air drops right here, as it starts moving this way, it's actually moving faster this way. So as it starts migrating there, it's like that water balloon that you throw out the window. If you're traveling this way and you have an object here, it's gonna throw right here. Like if I wanted to hit this idealized word right here, if I'm driving this way, I don't throw the water balloon straight at it. I actually have to throw it about right here because I know if I throw it, it's going to travel in this direction and hit the object. So when it hits right here, it's traveling in this direction much faster, and this is traveling slower. And so what happens is that object, like the water balloon, as it starts to travel that way, it's still moving this way, and so it tends to rotate and go on an angle. I hope that makes sense. This would be maybe easier to teach live in front of you, but I hope that you get the idea. So what happens is that this one, it will rotate this way because we're going from a slower rotation to a faster rotation. So as it moves down, this is moving faster, and so it does tend to rotate that way. This one, as it's moving that way, the actual object is moving faster this way, and it goes over slower ground, and so it tends to rotate this direction. And then when we have the wind way up here that hits the poles, it's going to rotate from right to left. Okay, these are ideal pressure belts. Ideal means this is the way it should look if everything was exactly the same temperature and we didn't have mountains and it was totally, the earth was smooth, it was glass, and there was nothing else going on. We have the same rotation. This is how everything would look. We would have air rising and sinking and rotating, rising and sinking and rotating. So it will make this spiral motion. Like if I was to take a slinky and move across here, and that it would make this round circular path all the way around. This one would do the same thing, but it would make a circular path all the way around this way. Well, when we look at the ideal picture here, all of the wind in this direction really is moving this way. And so we call these the trade winds. These are known as the trade winds. It should make some sense because, well, back in the day, when they had ships that relied upon wind for their movement around, they would come down. They didn't go from England all the way over to the Americas. They came actually down by Africa, and then they migrated over here to South America, and then they moved back up. Why would they do that? Because the winds were more ideal for them. If they come down here, they get this trade wind, or a wind that blows from east to west, picks up their sails and pushes them across, which is known as the trade winds, because that was a trade route. So they would do that. And then, why would they always come back up here to New York and then go back? Because the main wind belt here, known as the westerlies, goes from west to east. And so it just makes sense to go up to New York, head back to England, and have the westerlies push you that direction. Okay, and so our trade routes, if you look at early trade routes, they usually come down, back up and around, and they keep following this direction because they're following two things. Number one, they're following the wind currents, and they're also following the ocean currents, because the ocean currents are produced by wind currents. And so what happens is we have ocean currents that are going this way, and they rotate the Gulf Stream, and then it comes back up and back and around. And so our oceans are doing this, and our winds are blowing this way and this way. Hopefully that makes some sense. So when you're down in Florida, where do most of your storms come from? If you're right here in Florida, your storms are going to come in off the Atlantic Ocean and come in this way. Here in Utah, our storms don't come from the east, they come from the west. That's because we have this westerly belt here, and so ours come off the Pacific Ocean and come in to Utah, and they migrate and go from west to east. You go further south, and they go from east to west. And then if you go even farther north, we have what's called the polar easterlies. Now the polar easterlies will go from east to west. And since we have a really high Coriolis effect there, we get super high winds that blow. So we end up with really strong winds up there. Now, we call this the idealized pressure belt, but this is, remember, a flat earth, not flat earth, a smooth earth. We don't have a flat earth. This is due to a spherical earth that's totally void of mountains and valleys and just nice and flat and very uniform. But since it's not that way, we have a lot of mountains, we have a lot of valleys and other things. This is more what we get. Well, okay, I take that back. I forgot about this here. Let's take a look at what I have here. This just kind of shows you what's going on with the wind. So we have wind that comes down through here. This is our trade winds. This is our westerly winds, and they're going that way. And then you can see even further north up there, you can actually see where we have those polar easterlies. Okay. I hope you realize it's like 6 o'clock in the morning and I'm doing this. Okay, let's go on to the next one here then. This is the real wind system here. So notice that because we have our highs and our lows are going to be moving around. We have mountains in the way. Heat distribution is going to be different. And because of all this, we don't have these perfect lines right through here. Instead, we have this. Okay, you see we have a line right here that comes up and back down. So instead of nice and perfect, this is actually rising up through here and moving down. And these lines are really wiggly. They're not perfect. And this is how our real wind systems are. They're not perfect. They do move around. They're not, it's not ideal, which can make it really hard to make predictions as to how the weather's going to be. But this is how it really looks, is right over here. It's just like this, okay? I've got one more thing. I know this has been long. There's just a lot of stuff here. I've been in here probably almost like 15 minutes, almost 60 minutes now. Let's look at this last thing, and I think we'll call it good. Since we are talking about these belt systems, we got to talk about the jet stream, okay? What is the jet stream? The jet stream is the boundary between these wind systems. Okay, remember how in this video or this slide here, remember how I said it's not perfect? So we have maybe the Hadley cell and we have the Ferrel cell, and you look, it's not a perfect straight line, it's kind of wiggly, and we have this nice wiggle line between there. Well, guess what is found right in between those? The jet streams, okay? So we have two jet streams. We have the subtropical jet stream, and then we have the polar jet stream. We have two of them. Why? Well, because guess what's down here? This is the Hadley cell. This is the Ferrel cell, and then this is the polar cell, which is up above there. And the jet streams are found between where the air meets and either diverges or converges, and that's where we get these jet streams. And the jet stream, we follow the jet stream because it helps us to see what the Hadley cell is doing. We know it's not perfectly straight. We know that it is wiggly, and so it helps us to understand a few things. Now, remember that the jet stream moves. It moves up. The jet stream is going to move up and down because the cells do. Remember that animation I showed you where the Hadley cell migrates up and then it migrates back down? Well, guess what happens to these jet streams? They're going to migrate up and they're going to migrate down along with the seasons. So here's the one thing, if you ever watch the weather and you watch them, they pay real close to the jet stream, especially here in Utah because we are located about right here, and the jet stream can drop and it can go back up. Well, if we're right here and this subtropical jet stream right here rises up and it goes above Utah, what can we predict the weather to be like? Well, the Hadley cell is probably going to have warmer air. It's probably going to be a little bit more moist. So here's one little thing you can look at that. For Utah, the air below the jet stream here is warm and the air above it is cold. And this one is going to be the same. It's going to be warm here and cold there. And you're like, whoa, wait a second. if I have warm here and cold here, well, you got to realize it's the same temperature, but this is going to be cooler than this is here, and this up here is going to be cooler than this here. So if we're watching the jet stream and the jet stream comes up, then we can expect warm weather. If the jet stream drops down below, then we can expect colder weather. And if we know that it's a polar jet stream and it comes down, we can expect really cold weather. We're talking about Arctic air that is coming down into the Utah region. So we like to pay attention to the jet stream. The jet stream can split, it can separate. The jet stream is just basically a band of air. Let's see if I have a picture of it here. So as you look here, we can see we have the Hadley cell, the Ferrel cell, and the polar cell. And if you look, you can see how it rises up and then it begins to sink. Okay, the jet stream here is this region where these two cells are colliding into each other. And we end up with this nice little area, and it can be like 100 feet wide to 200 miles wide. It can be, it's just, think of it as like a river or a river of air that just flows in between this and it moves along here. And the same is true for up there. Planes like to fly in this stuff. In fact, one of the first times we ever found the jet stream was during World War II, I believe. Yeah, World War II. So we were flying planes from the U.S. to Hawaii, and we were trying to get to Japan, but we could never get there because for some reason, as we flew out there, we'd always run out of fuel. We just couldn't make it. But then on the return back from Hawaii to the U.S., we always had more fuel than what we had going back. And there's only one reason, because when they were flying from here to Hawaii, they were actually flying against the jet stream. So they were flying against the wind. But when they were flying back, they were flying in the jet stream, which they didn't have any resistance there, and they were able to fly without using more fuel and at a faster rate, actually. And so that's where we started noticing the jet stream. The Japanese, one of the things that they did, which is kind of smart in ways. I mean, when you're in war, you're thinking of how you can attack your enemies. And I don't know if I told you this or not in class, but they did actually launch a bunch of balloons that had bombs on them and launched them up into the air to follow the jet stream. And the jet stream, they were hoping that the jet stream would pull them across the Pacific Ocean and drop them over in the right over here, the northwest. And we have found some bombs that were from this. Most of them didn't make it because they fell into the Pacific Ocean. But there were one or two that did make it, and I think only one actually went off. The other ones did not. But anyway, for whatever it's worth, we can even use weather for war, which actually we do a lot. So here's that picture I was talking about earlier, is that we have these jet streams here. So you look at the one that is here. This is our summer jet stream. Okay, and this is our winter jet stream, and they will drop. So our jet stream in the summertime, this actually moves on up and we get nice warm air. But then as winter comes around, this jet stream will drop, and it drops. If it drops down low, then we tend to get colder air. So this is going to be warm, this will be cold. Summertime, this will be warm and this will be cold. So we pay close attention to the jet stream and where it is in our location, and it will help us to see what the weather's going to be like and what's going on with our seasons. Okay. Yes, we're done. Sorry, this did take long. I don't know what more to do. I'm trying to make this as quick as I can, but there is just a lot of material here for us to go over. Guys, enjoy. I hope if you have questions, please let me know. I'd be more than happy to help you out with whatever I can through email. I've even thought about possibly doing a Zoom with you guys, if that might help you out as well. Help you to answer questions that you might have. There is another part that we'll be doing with this. It has to do with air masses, so watch for another video here soon about air masses. And then after we get done with that, we'll be having, I believe, a test and a quiz. And I will post those on Edmodo, so make sure that you are staying up to date with things. I can't make you watch these things, but I hope you are. I wish we were here together, but we're not. So here's a long distance. Love you guys. Hope things are going well. Take care, and I'll see you in the next video.